We are discussing the topic of phase transformation, and we discussed nucleation in particular. There are two kinds of nucleation, homogeneous and heterogeneous nucleation. I did not mention this before, but let us discuss this. What we have been discussing till now is like the formation of a solid nucleus inside a liquid. This is an example of homogeneous nucleation. We did not use this adjective before, we were simply calling it nucleation, but this is an example of homogeneous nucleation, which essentially means a nucleation unaided by any surface or defects. We took this up because it is mathematically simpler to analyze. However, in reality this is a quite unlikely situation. A more likely situation for nucleation to happen, particularly in the case of freezing, is that nucleation will happen at the container wall. So, the solid may form at the wall of the container. This kind of nucleation is called heterogeneous nucleation. Heterogeneous nucleation. This kind of nucleation is aided by some surface, for example, like in this example, container wall, or in case of solids it can be grain boundaries. Or it can be other defects such as dislocations, or vacancies. So, this kind of nucleation is called heterogeneous nucleation, and it is a more common kind of nucleation. Mostly, for example, in this situation itself, you can see in case of solidification, it is quite likely that nucleus will form at the container wall rather than totally inside the liquid. So, homogeneous nucleation is a nice simple situation, easy to analyze mathematically, and in a study in laboratory situations can be created such that we have homogeneous nucleation, but most practical nucleation situations are heterogeneous nucleation. So, let us look at heterogeneous nucleation in a little bit detail. Just like we analyzed homogeneous nucleation in terms of energy, let us do a similar analysis for heterogeneous nucleation. Let me assume some sort of container wall or substrate. over which there is some phase alpha and let me call the substrate itself delta, and in alpha a nucleus of beta forms. Alpha is transforming in beta on this surface of delta. So, that is why it is a heterogeneous nucleation. And in particular, again just like we simplified the geometry of the problem in homogeneous nucleation by considering a spherical nucleus, here again we are simplifying the geometry by considering a spherical cap nucleus. So, essentially we are saying that beta is forming as a spherical cap, so spherical cap of beta in alpha on delta. So, by spherical cap I mean that the surface, the alpha beta surface is spherical, and I have tried to draw the entire sphere here. So, you can see that this sphere is cut by the surface of delta. So, only a small portion of the sphere, and that is what is spherical cap, is acting as the nucleus. So, the center of the sphere and the radius as r. Now, three kinds of interfaces are involved here, and they are meeting at a junction like this. So, you have for example the alpha beta interface, and I am showing the surface tensions by these arrows. So, this is gamma alpha beta, and this is another surface between beta and delta. So, this I write as gamma beta delta, and you have a surface between alpha and delta, which I write as gamma alpha delta. Since these three surface tensions are locally in balance at this point, we can write an equilibrium condition for these surface energies in terms of gamma alpha delta. If I take the horizontal component, then gamma alpha delta will be equal to gamma beta delta plus gamma alpha beta cos theta, where theta is this angle here, also known as the contact angle. Now, to carry on our analysis, we need the volume and surface area of this spherical cap. This can be easily derived using calculus. We do not do that here, we just write the result, but I encourage you to go ahead and try to derive this using calculus. 4 by 3 pi r cube. So, the volume of this nucleus, which I am calling V beta, is 4 by 3 pi r cube, which is the volume of the sphere, times a factor depending on theta. You can see that the way we cut, depending on where we cut, the theta will change, and correspondingly the volume will change. So, S theta will obviously vary from 0 to 1. So, when you derive this, you will get the form of S theta also. Let me write that. So, S theta is 2 minus 3 cos theta plus cos cube theta by 4. This function so let us plot S theta. This is 1, this is 0.5 and this is 0, and the contact angle theta varies between 0 to 180 degree. So, if you look at this function, it will be 0 at theta is equal to 0, it will be 0.5 at theta is equal to 90 degree, and it will be 1 at theta is equal to 1 at theta is equal to 180 degree. It will be 1 at theta is equal to 180 degree, and in between it takes a sigmoidal shape, something like this. So, volume of the spherical cap depending upon the contact angle can be any fraction of the volume of the full sphere, and that fraction is given by this S theta, which depends upon the contact angle in this way. We also require the surface area of the spherical cap. So, that is the interface between alpha and beta. So, that area I call A alpha beta, and that can be shown to be 4 pi r square 1 minus cos theta by 2. And similarly, I require the area between beta and delta, that is the base, circular base on which the spherical cap is sitting. So, that circular base on which the spherical cap is sitting, A beta delta, is pi r square 1 minus cos square theta. So, we have all the geometrical parameters, the volume of the spherical cap, the curved surface area of the spherical cap A alpha beta, and the horizontal base, the circular base A beta delta in terms of r and theta, the radius of the spheric sphere and the contact angle theta. So, with this we can take our next step of developing the energetics. So, recall that we can write the energy of formation for the heterogeneous nucleation, for the heterogeneous nucleus, that will be volume of the nucleus, which is V beta, times the free energy per unit volume of beta minus the free energy per unit volume of alpha. Again, we are assuming that there is no volume change between beta and alpha. So, the same volume of alpha transformed into beta. So, we generated so much of free energy V beta into G beta, but we lost V beta into G alpha. This is the volume energy term. Then we have surface energy terms, and now there are 3 different kinds of surface energy terms as you saw. So, we have A alpha beta, that is the curved surface of the nucleus, that is this surface A alpha beta, times surface energy per unit area of alpha beta surface. So, A alpha beta, gamma alpha beta. We also formed the base of the nucleus, which is A beta delta, gamma beta delta. But then when we created this surface, recall that when we created this beta delta surface due to nucleation, before nucleation this same surface was alpha delta, because alpha was filling this entire space. So, the amount of area which we created for beta delta, same amount of area was removed from alpha delta. So, let me not write this as alpha delta, let me keep writing this as beta delta only, because the area is the same, but the surface energy is alpha delta. So, this is an important. So, recall that in homogeneous nucleation the volume energy was the driving force. So, here also volume energy is the driving force. And there the surface energy was barrier to nucleation. Here also surface energy is barrier to nucleation, but one surface term, since it is getting deleted, since it is being removed, this surface term also acts like a driving force. So, there is an additional driving force in terms of surface energy, because nucleation is happening on a surface. So, that particular part of the surface is getting removed from the system. So, this is the energy expression, and if you recall, we have all these terms V beta, A alpha beta and A beta delta in terms of r and theta. So, we can express that. So, this is a function of r and theta. And we can again think of the variation of delta GF as a function of r. So, we will find that this variation again is somewhat similar to the homogeneous nucleation, and we can get the critical nucleus size by a similar condition that delta GF heterogeneous by del r is equal to 0. At r is equal to r star. So, when you express all these as a function of r theta by substituting those expressions which we derived in the previous slide. So, and then differentiate, you can find the critical radius for heterogeneous nucleation. And rather interestingly, when you will do this algebra, I am not doing it here, leaving this as an exercise for you, but you can do that and convince yourself that this r star heterogeneous, at which this differential coefficient is 0, turns out to be minus 2 gamma alpha beta by delta G V. Delta G V is again this term here, G beta minus G alpha is delta GV. Change in volumetric free energy, change in free energy per unit volume when the transformation happens from alpha to beta. So, final minus initial, that is delta GV. So, if you look at this expression, you see that this critical radius for heterogeneous nucleation turns out to be exactly the same what we had found for homogeneous nucleation. There we were thinking in terms of solid and liquid, so that was gamma solid liquid, but in a more general case it will be gamma alpha beta. So, the critical radius for heterogeneous nucleation is exactly the same as critical radius for homogeneous nucleation. However, there is still a difference, because recall that in homogeneous nucleation the entire ball, the entire sphere of radius r was the nucleus, but in this case only a part of the sphere is the nucleus. So, still although the radius appears to be the same, the volume of the two nuclei will not be the same. So, if we look at it in terms of volume, then we find that the volume for heterogeneous nucleation is not equal to volume for homogeneous nucleation. It is different by the same factor S theta which we had derived in the, since obviously since you have derived this expression, V beta is 4 by 3 pi r cube S theta, and this was the volume of the entire sphere, and S theta was the factor by which volume of the beta was different from the volume of a sphere. So, that same S theta will be true for the volume of critical nucleus also. So, the volume of critical nucleus will be smaller than for heterogeneous nucleation, will be smaller than volume for the homogeneous nucleation by this factor S theta. And since S theta is always less than 1 except for theta is equal to 180 degree. So, depending, and theta is the contact angle. So, smaller is the contact angle, smaller will be the volume of heterogeneous nucleation. And you can see the point that for nucleation we have to assemble so many atoms in the form of a new phase, and that is the initial difficulty of nucleation. So, smaller is the volume or smaller is the number of atoms which we have to assemble, easier will be the nucleation process. So, if S theta is much small, if the contact angle is small, S theta will be small, and then the volume of heterogeneous nucleus will be correspondingly smaller than the volume for homogeneous nucleation, and thus heterogeneous nucleation will be easier. We can try to draw this. Recall that in homogeneous nucleation we got a curve of this shape for delta GF. The maximum we can call that as delta GF star, and the radius corresponding to that is r star. Let me call this r star homogeneous. So, this is for homogeneous nucleation. If I superimpose the curve for heterogeneous nucleation in the same, we found that R star is the same. So, for heterogeneous nucleation also we will get the maximum at the same value. For heterogeneous, this was delta GF star for homogeneous, and as we saw R star was the same. So, this is same as so you can think of this energy. Initially the energy of the system has to increase. So, this is a kind of energy barrier for the nucleation, and this energy barrier for nucleation also will be lower for heterogeneous nucleation than for the homogeneous nucleation, and if you derive the expressions for these, this will turn out to be again smaller by the same factor S theta which we have been using for the volume. So, delta GF star for heterogeneous is delta GF star for homogeneous times the same factor S theta, and we have already seen that V star for heterogeneous, V star for homogeneous times S theta. So, smaller is the contact angle, smaller is S theta, and smaller is the volume of heterogeneous nucleus. So, you have to assemble lesser number of atoms to form the heterogeneous nucleus. Similarly, the energy barrier for nucleation, that extra energy which is required for nucleation, is also less for heterogeneous nucleus by the same factor. So, both these facts aid heterogeneous nucleation. So, heterogeneous nucleation is favored nucleation for smaller contact angles theta. So, smaller is theta. As theta decreases, both V star heterogeneous and delta G star heterogeneous, both of these decrease. This is what in physical term, smaller is theta, we say that better is the wetting. So, if the nucleus wets the substrate or the wall on which it is forming, then heterogeneous nucleation will be favored.